Hello everybody and welcome to our first Physics of Music online lecture. I'm hoping that as I get to know Zoom better, I might be able to do this live on Zoom, but at the same time I think it might be nice to have a video where you can go back and repeat stuff. So we'll see how it works, and I promise it will get better, but it's been a slow ramp up. What I wanted to do today was give a little hint on homework 7, which is due next Tuesday. I believe that's March 31st. And then we'll review longitudinal standing waves. We'll do some problems on it. I'll look at a quick example of the activity we did, and we'll also look at a video. Okay, so on homework 7, on stringed instruments, the last question, so I'm going to do a problem similar to question 4. I believe in question 4 it talks about like what are known as harmonics or artificial harmonics on a guitar. If you pluck the string and let it vibrate at its full length, you get a certain note name. But if you touch softly onto the string and then pluck it, you will get what's called a harmonic. And what you're basically doing is you're making the point on the string where you touch it a node. All right, so for example, let's say this is the look of the fundamental envelope for the string. It's not too beautiful, but there it goes. And let's say here, this frequency F1 of this fundamental of the string, let's say it's 100 hertz, 110 hertz. I think that's my A string, the 5th string on your guitar. Okay, now if you go ahead and say touch string softly at, let's go ahead and say 1/3 of its length from the end. Well, at that point, you're going to get a node. And what's important is that a loop will form, right? This is a single loop with a node here, an antinode here, and a node here, right? So you touch string at 1/3 of its length, let's say right around here, you'll form a node there. A loop will form between this point and the end of the string. Point touched. And end of string. And the idea then is that, oh, well, if I touch the string right here at 1/3 of its length and I form a node there, and the size of the loop is from that node to the end of the string, then the loop, one loop will equal 1/3 of the string. One loop length equals 1/3 of the string length. Right? And so because the standing waves have to have loops that are all the same size, there's going to be 3 loops that form on the string. So I'll show the equilibrium position again of the string right here, and then I'll just go ahead and do my best guess and say this is 1/3 of the length. And well, then there'll be another node at 2/3 of the length or at the other third. Then there'll be, of course, a node at the end. So the idea is that if you touch a string at 1/3 of the length of the string from the end, you've formed a node that is 1/3 the length of the string. Excuse me, a loop that is 1/3 the length of the string. Because loops are always the same size, you're going to have 3 equal length loops. I didn't draw this so wonderfully. Maybe I could work on it a little bit better again. Regardless, I can't help my obsession to get it perfect here. But let's say that's it. Well, what does the envelope look like? The envelope is going to look like this. well, as best as one can draw it. Right? And so now you have a node, antinode, a node, antinode, node, antinode, node, right? 3 loops. What mode is that? That's the n equals 3 mode. And we know that the frequency of the n equals 3 mode is equal to 3 times the frequency of the first mode, right? Because the harmonic series that the nth frequency, standing wave of the nth mode frequency, is equal to the mode number times the fundamental. And so the easy answer is, well, if F1 is 110 hertz, then F3 is 3 times 110 hertz, or 330 hertz. Now in your problem, you touch the string at 1/7 of the length from the end. How many loops are going to form? How long is the loop compared to the string length, right? I don't give you any numbers for the string length. So what you need to understand is, a loop is going to form where I touch between where I touch the string and the end. And all the other loops have to be the same length, the same proportional length of the string. So I'm hoping that is a helpful hint. So I took an image of that and I will post that as part of this online lecture. Okay, so what I wanted then to get to, let's see if I can get myself a new blank, that's nice, is to remind ourselves about the longitudinal wave and the transverse wave representation of longitudinal waves, right? So we started off here with a tube closed at both ends. Air is not able to move at a closed end, and so there must be nodes at that end. To make a standing wave, I'm going to have at least one antinode, because antinodes are adjacent to nodes, period. And so this is a half of a wavelength of the first mode. And you can see how with the transverse wave, everything kicked to the right, everything equilibrium, everything kicked to the left. Okay, so we got rarefaction, compression, and then it reverses itself. We go to the next one, right? So we're forming this standing wave with nodes at the end, and everywhere there's a crest, we've moved everything to the right. Everywhere there's a trough, we move everything to the left. Continue on to the third mode of oscillation, right? We have 3 loops, and as they oscillate back and forth, the air or the water or whatever the material is for the longitudinal wave sloshes back and forth. And wherever you have the node, the particles move 0 here. Wherever you have the antinode, the particles move the most, and at the node, you still have no motion. Even though we form a rarefaction here, the idea is at this point, none of the air has moved at all. At this point, none of the air has moved at all. It's just which way is it moving. Okay, anyway. So 3 half wavelengths fit for the n equals 3 mode on the string. So here we wrap it up. I say string, right? Because it looks just like a string. It has the same equations of motion. The length of the string has an integer number of half wavelengths, or the wavelength of the mode n is 2 times the length. I'm just solving this for lambda n divided by n. All integers, non-zero integers. Frequencies go the same way. Using f is v over lambda, f equals v over lambda over 2L over n. And so I just rearrange it. And so recognizing v over 2L is the fundamental frequency, f1, this is 1, f1 is v over 2L, then all the other modes are harmonics of the fundamental, integer multiples of the fundamental frequency. And the important point is tubes of air closed at both ends form standing waves with identical mode shape and equations for the frequency and wavelength for the standing waves on a string. So it's kind of an interesting and cool thing. Okay, tube opened at both ends, actual flute or other woodwind instrument. Air is freest to move at each end. That's where the antinodes have to be. You have to have antinodes at the open ends. And for the lowest frequency standing wave, you're going to have a node between the two, so that a node is adjacent to an antinode only, right? And so when we look at how things happen, Well, this is a loop length technically. A loop is a node to node, but an antinode to an antinode is also half a wavelength. And so we form half a wavelength here. And basically we form a compression in the center, or we form a rarefaction in the center. And they often call this a breathing mode because it takes air in and it pushes air out. This is pretty much what most of your woodwind instruments and brass instruments mostly are doing, playing in the fundamental. Let's increase the frequency. We're going to add a node-antinode pair with still antinodes at the end. Now the distance between two adjacent antinodes, just like two adjacent nodes, is half a wavelength. So we see a full wavelength is supported in here. And this is what the motion looks like. It's just that we have to use this transverse wave representation to talk about this kind of motion because it's just too complicated to write down, right? And so we show the envelope of this transverse wave indicating essentially how the longitudinal transverse wave is working. Here is the third mode. Add another antinode-node pair. You're breaking the tube up into smaller and smaller pieces. Here's half a wavelength. There's 3 half wavelengths in the n equals 3 mode. That should be n, not b. And here is what it sort of looks like. It's nice to be able to see how it works, compare it to the transverse wave. All right, enough of that. To summarize, these are the envelope patterns of the first harmonics, the fundamental, second and third mode, for a tube open at both ends. Here's the antinodes, here's the nodes, right? And the idea here is, using the math, identical mathematics, because basically the length of the waves are the same. Even though you have antinode on each end, you could think of taking this, slicing it off, and attaching it here, and it would look like a fundamental. It would look like just this little piece here, but over the whole length of the tube. So actually, this is a quarter wavelength, antinode to node, and here's another. So there's 2 quarters or half a wavelength. Here's half a wavelength, here's a quarter from here to here, and here to here. That's a whole wavelength. Slice this part off, attach it over here, and you would see 2 loops as you would expect on a string. So the symmetry is a little bit different. It's sort of symmetric, but now we have antinodes at each end. Still, the mathematics is the same. Different mode shape for the tube, the tube closed at both ends and the string, but the same equations for the standing waves. Here is where things get interesting. Tube closed at one end, open at the other. We have to have a node at a closed end. We have to have an antinode in another. And this would be the lowest frequency because we have a node adjacent to an antinode. No worries. So in this case, what we're doing is node to antinode is quarter wavelength. It's node to node or antinode to antinode that's half. So here's a quarter wavelength that fits. And so this is what happens. We squish all the air in, we let all the air out. This is also what they would call a breathing mode. You take air in, you take it out. You form rarefactions or compressions at this point. And the frequency of that happening is the frequency of the standing wave that you might hear. Here's the second mode. Antinode at open end, node at closed end. Fit another node-antinode pair to keep things symmetric. Node next to an antinode, and good enough. Move on. Well, here's a quarter of a wavelength. We're calling this the third mode because it turns out 3 quarter wavelengths fit in this tube. And so we have this funky shape. Right? Just remember, we want to look at this transverse wave picture and be able to look at that transverse wave picture and understand about what's happening here. Okay? The next allowed mode, well, we have an antinode at each end, at one end on the open, a node at the closed end. We have 2 antinode-node pairs in there, equally spaced. So by definition, here's a quarter of a wavelength right there. But there's 5 of them, so it's the 5th mode. The odd modes are not supported. The even modes are not supported, only the odd modes. And here's what the complex longitudinal standing wave pattern looks like. Pretty exciting. Okay, but again, it's that transverse wave picture we really want to look at. So here's a summary again. These are the transverse wave envelope patterns that are supposed to represent the longitudinal standing wave. Node, antinode. 1/4 of a wavelength fits in the n equals 1. N equals 3. You have 1 to 3/4 of a wavelength. So 3 quarter wavelengths. Here's the fifth mode, 1, 2, 3, 4, 5 quarter wavelengths. So that's what we talk about with the modes, only the odd modes supported. Only odd quarter wavelengths can fit in the tube. So you take a look at the equations. They're identical except for one thing. There's a 4 everywhere instead of a 2. That's the only difference, and the fact that the n values can only be odd integers. Right? So they form standing waves with asymmetric mode shapes. The equations for the frequency and wavelength of each mode are similar, but you need to replace 2 with a 4. So that's really all that you need to worry about. All right, I want to do an example, but maybe it's a good time now to look at a little video. So I have a nice little video here I'd like you to check out.
Okay, this is a demonstration of organ pipe modes of vibration. You may already be aware that a longer organ pipe, this is open on one end and also open on the other end, and this is where the air is introduced. Then there is a knife edge made out of wood that the stream of air goes through this hole against the knife edge, and then there's an instability when the air is incident on a knife edge. This instability will cause a puff of air to come out outside of the pipe, and then a puff of air to go inside the pipe, alternating outside and inside. And there's a particular frequency that's associated with this instability. And if that frequency matches the length of the pipe, then you'll get a resonance in the pipe. Like that. If you move to a shorter pipe, it's built the same way. The length is shorter. You get a higher sound, and even shorter. You can, if you blow hard enough in here, force different modes to sound in the pipe. What we were hearing just then is the fundamental mode, the lowest possible frequency that this pipe will produce. But any pipe actually produces a sequence of frequencies that follow at least approximately the harmonic series. So this is the fundamental, the lowest possible frequency. If I blow a little harder, I get a mode that, for those of you that have musical background, will recognize as approximately an octave above it.
Twice
Do the same thing on this one. So we get a lower mode, a higher mode, and then there's actually an infinite sequence of these modes that goes up to infinity, and that gives the organ pipe its character, its characteristic sound. As I mentioned before, all of these pipes that I've shown you so far are open on both ends. If you ask what happens when you close one end, and I'm just going to put my hand across it to close this end, then, well, first I'll do it with it open, then close it. So you'll notice that the sound is lower. In fact, if you ignore end effects, then the theory predicts that the sound is actually 1 octave lower, the frequency being half of its original value.
Just a quick interjection. The tube opened at both ends, and it's fundamental. Half a wavelength fits in the tube. Now he closes the end, right? And 1/4 of the wavelength fits in the tube. The tube is the same length. So in the open situation, the wavelength is twice the length of the tube. But in the open closed, where he closes one end, the wavelength is 4 times the length of the tube. And so if you double the wavelength, you have halved the frequency. You've decreased the frequency by half. You've gone down an octave. That's the point.
That is the reason That's the reason why a clarinet sounds lower than a flute does. Flute and clarinet both have about the same length. The flute is open on both ends, but the clarinet, the mouthpiece end, is effectively closed. And so the lowest notes you can produce on a clarinet are much lower than the notes that you can produce on a flute. That's organ pipes.
Thank you, sir. So that was a pretty interesting video. It was nice to be able to show you a demonstration considering you're not here. Okay, so I wanted to do some examples because you've got a homework number 8 that'll be coming out, and these two examples will follow directly along that line. So for homework 8, so I'm just going to say similar to homework 8. In the first two problems, you got to draw the standing wave envelope patterns, right? The transverse standing wave patterns like I just showed you in the PowerPoint. But you're going to have tubes open at both ends and then open only at one end. So you got to be careful, take a look at the notes, look at the books, etc. to draw the right envelope. But then it gives you a length and it gives you the speed of sound, etc. and asks you to calculate it. So I just wanted to kind of go over it quickly. So I want to do a tube opened at both ends. Sometimes you'll hear it called an open tube or just an open tube. A tube opened at one end is often called a closed tube, or an open closed tube. So I'm going to give you, in general, this is going to hold for both, the length of the tube is just like that demo I did in class, I think the lecture before our last one, where I took a speaker and I placed it next to a tube and I changed the frequency of the speaker. Well, I was using a tube about 1.3 meters long, right? The velocity of sound in air is 345 meters per second. And the idea is, given the length and the velocity, find lambda and frequency of first 3 allowed modes, or allowed standing wave patterns. Let's remember our equations for tubes open at both ends. We have the wavelength of mode n is equal to 2L over n. And we have the frequency of the nth mode equal to the mode number times the fundamental, where the fundamental frequency is v, velocity of the waves, speed of sound in air, over 2 times the length. So let's go ahead and give it a whirl. Lambda 1, well, it's 2L over 1, which is just 2 times 1.30 meters. And so that's 2.6 meters. Lambda 2, right? And what's important here is to remember, oh, integers, 1, 2, 3 are your first 3 allowed modes. Lambda 2 is 2L over 2. 2's cancel, so it's just equal to L, the length of the tube. And lambda 3 is 2L over 3. So I'll just put in the 1.30 meters over 3, and if you do your work, you get 0.867 meters. All right, what about the frequencies? Oops, 0.867 meter. Frequencies. The fundamental is V over 2L. That's 345 meters per second over 2 times 1.30. Do the math, and you should find about 132 hertz. Now you could go ahead and say, oh, F3 is 3V over 2L, but it's just easier knowing the fundamental. Did I say 3? Let's do F2 first. It's just 2 times F1. 2 times 132, right? So once you have the fundamental, you know the rest of the harmonic series for this guy. 2 times 132 is 246 hertz. And last, F3 is 3F1, 3 times 132 hertz, which ends up being 396 hertz. So as the gentleman was just showing, if you took a tube, opened at both ends, 1.3 meters long, and you were able to excite the first mode, you'd get this frequency. If you blew harder into it, as he was showing, you might be able to excite the second mode at 246. If somehow you were able to really push hard on blowing over that knife edge, somehow you could get to the third mode in 396 hertz. This is how a bugle works. There's no keys. It's all the same length. You just blow harder, blow differently, and try to get more energy into the tube, and it jumps up to the next mode, and so you're able to play different notes. So jump here from here to here is an octave. From here to here is a perfect fifth. From F1 to F3 is an octave and a perfect fifth, etc. Okay, so that's all we have. We're done with the tube open at both ends. How about tube closed at one end? Well, same idea. Find lambda and frequency, wavelength and frequency of first 3 allowed modes. Well, remember our equations. How are they different for a tube closed at only one end? Replace the 2 with a 4, 4L over N. The frequency, same idea. The frequency of the nth mode is the mode number n times the fundamental, where F1 is V over 4L. Right? Do our wavelengths. Lambda 1. Oh, hang on. Remember, first 3 allowed modes, odd numbered modes only. Right? We're not going to do the 7, we're going to do the 1, 3, and 5. So lambda 1 is 4L over 1, which is 4L. Four times 1.3 is 5.20 meters, right? So what I've done is I've taken the same length tube, kept it open at both ends, somehow excited the first mode, and that was 132 hertz. Excuse me. It had a wavelength of 2.6 meters. Now, take the same dang tube, put a cap on one end, excite it to its first mode, and you'll find out the wavelength of that mode is 5.2 meters, twice that wavelength. Bigger wavelength, lower frequency. Go down an octave. Lambda 3 is the next allowed mode. And so that's 4L over 3, basically 4/3 the length. 4 times 1.30 meter over 3. Do that calculation, get 1.73 meters. All right, go up, increase your wavelength, decrease your wavelength, increase your frequency. The next mode to find is lambda 5. That's the next allowed one. That's 4 times L over 5. Four-fifths of 1.30 is 1.04 meters. So the wavelengths get shorter, and as we'll see, the frequencies get higher. Excuse me. F1 is V over 4L. That's 345 meters per second. Oops, I think my pad is getting a little weird. Over 4 times 1.30 meters. Pardon that. Oops. We'll just leave that alone. 345 meters per second over 4 times 1.3. Do the math. You'll find 66.3 hertz. And I think we had theoretically calculated that when we were actually doing the demonstration. The next allowed mode is the third mode. And that is 3F1, right? 3 times 66.3 hertz. Do that math. What do you find? 199 hertz. Uh-oh, my pen is giving out. I think my pen has run out of ink. No, it's just acting a little weird. Last is F5. That's going to be 5 times F1, 66.3 hertz. Multiply 66.3 by 5, you get 331.5. I'll squeeze in my units below it. All right, so hopefully my first hint was helpful for the question on homework 7. We reviewed standing waves in tubes, closed at both ends, identical to a string, open at both ends, same as a string, but different shape mode, and closed at one end, asymmetric, so you get these only odd modes left. Okay. Look out for that homework assignment, and we will find a time in the next couple days to basically try to do a Zoom conference meeting. Ideally, it would be Thursday. We'll try. I might have to wait, and I might postpone the homework. Don't sweat it, people. We will get through this, and I will be beyond understanding, okay? So take care, and we'll see you next time.